Okay, still on applications of Newton's second law of motion. I'll be applying that law to look at this particular question. A block of ice slides down a 45 degrees inclined plane in twice the same time it takes to slide down a 45 degrees frictionless inclined plane of the same length. Now the question says, what is the coefficient of kinetic friction between the ice block and the plane? Okay, let me just illustrate it using these diagrams. It means that there are two different inclined planes of the same length. Okay, one of them is smooth, the other one is having some frictional force acting between the plane and the ice block. Okay, let's say this is a block of ice. Okay, so let's call this one the smooth inclined plane. There's no frictional force acting between the surface and the block of ice. That's assuming the frictional forces are negligible. But in this case, the frictional force is not negligible between the ice block. Let's call the mass of the ice block M, and that's of course the same ice. And the length of the planes is the same, whether for the rough plane or for the smooth plane. And both planes are inclined at angle 45 degrees with the horizontal. That is, for the two situations, the angle of inclination of the planes is 45 degrees. Now, let's say it takes a time t for the block to slide through the smooth inclined plane. That's the time taken is t. Then the time taken for the same block of mass to slide through the rough inclined plane is 2 times t, from what the question says here. Let's say t is 5 seconds. Then you're going to take 10 seconds for the same block to slide through this rough inclined plane. Okay, let's draw the free body diagram for these two different planes. Here we have the weight of the block, that is mg, acting vertically downwards, and we have the normal reaction, the normal force n, and then we have the component of the weight. Of course, you know this from my previous videos. There's always a component of the weight that acts down the plane, parallel to the plane. We'll call that the mg sine theta. Here on the rough, we also have the weight of the block, mg, and then we have this component of the weight of the block, mg sine theta, that acts in a direction down the plane. We also have the normal force acting at right angles to the plane. Okay, in the first case, there's frictional force. The kinetic frictional force is zero because the plane is smooth. So the only force acting along the direction of motion is mg sine theta according to Newton's first law of motion. Now in the second case, frictional force opposes the motion. Let's call that the kinetic frictional force opposes the motion of this block of ice that slides down the rough inclined plane. Okay, here let me write down the equation using applying Newton's second law of motion. F equals ma. Okay, the only force acting is mg sine theta. That's the only force acting along the direction of motion. So I'm going to equate mg sine theta. I equate that to ma. That is to say the resultant force, which is mg sine theta. Okay, that's the resultant force equals ma. So this mass cancels out this mass. So which means I can call this the a1, the acceleration of the ice block while falling through the smooth inclined plane. So my a1 is g sine theta. Okay, I call this equation 1. Now let me come back to the second inclined plane where the frictional force acts. The resultant force from Newton's second law is T mass times acceleration of the block down the plane. And here the resultant force is given by the difference between these two forces. So mg sine theta is taken as positive because it acts in the direction of motion. So any force acting in the direction of motion is given a positive sign, and any force that opposes that direction is given a negative sign. Minus Fk from Newton's second law, the resultant force equals mass times acceleration. Let me call that A2, the acceleration to the rough. So we're going to see how the two accelerations relate, A1 and A2. Okay, so let me come back here now. And for one of the equations of motion, I have that the distance traveled, which is the length of the plane, equals ut plus half at squared. Okay, I'm going to employ this equation too to get the job done. All right. Okay, since the block starts sliding from rest, this term is 0. So the length of the block, which is the distance s, is given as half a t squared. So let me use this equation for the first instance and then for the second instance and see how the two acceleration relate. For the first instance, the length of the plane is half times a1 times t. For the second situation, it is L equals half times a2 times, okay, sorry, this is squared here, times 2t squared because it takes 2 times t, twice the time, you know. So the length of this plane is half times a2 times 4t squared, while this is length equals half a1 t squared. So since the two lengths are the same, so it's proper to equate these two equations, that is equate this to this. Since L equals this L, therefore means that half a1 t squared is equal to half a2 times 4t2 squared. Alright, so this cancels this. T squared cancels t squared. Okay, so in terms of the equation given to me, what is a2 in terms of a1? A2 therefore is equal to a1 over 4. Okay, so let's call this equation 2. Alright, so I hope you have been following what I've been doing for some time now, trying to solve this particular question. Okay, so to continue solving this question, this equation, I'm going to bring it out and rewrite it here. Mg sine theta minus kinetic frictional force equals Ma 2. So I want to rewrite that here so that I have mg sine theta minus the kinetic frictional force equals Ma2. Okay. Now, let me bring the relationship between the two accelerations. A2 equals A1 over 4. And also we know that A1, we have that here, that A1 is what? G sine theta. Okay. So I write it down there as A1 equals G sine theta. Okay. Now, I'm going to make substitution for A2 and also for A1 so that I have mg sine theta minus fk equals m. My A2 is what? A1 over 4. Okay, so I have mg sine theta minus fk equals m over 4 into g sine theta, because I already know that my A1 is g sine theta. Okay, so I want to make fk the subject of this equation. So I'm going to have fk equals mg sine theta minus m over 4, or mg sine theta divided by 4. Okay, when I subtract that, what is my fk? It's possible to find a difference between the two of them, and that will give me, this is like saying 1 minus 1 over 4. That gives 3 over 4. 3 mg sine theta divided by 4. Okay, because this is 1 minus 1 over 4. 1 minus 1 over 4 gives me 3 over 4. Okay, and Fk from the loss of frictional force is mu k, that is coefficient of kinetic friction, multiplied by normal reaction. And my normal reaction is what? Mg cos theta. Of course, you know that from my inclined plane, that the normal reaction here is balanced by mg cos theta, because there's no motion in this direction along the y-axis. Okay, so we continue from there. We have here that looking for this now. So I have 3 mg over 4 sine theta equals mu k times mg cos theta. Okay, so my mg cancels out mg. I have 3 over 4 sine theta is equal to mu k cos theta. So dividing both sides by cos theta, I have 0.75 because that is my 3 over 4 sine theta over cos theta equals mu k. Okay, so that gives me tan. The ratio of sine of an angle to the cosine of the same angle is always tan theta. So I have 0.75 times tan theta equals this. That means tan 45, because theta was given as 45, 45 equals mu times k. Tan 45 is 1, that gives us 75, which is equal to this. So that gives me the coefficient of kinetic frictional force acting on the surface. Okay, so that gives me the solution to this problem. All right.